Kent Hovind claims that due to the inverse square law, the moon would have been right on top of the Earth 1.2 billion years ago and ruining the Earth with the tides. I did this in another video, but I wanted to go into a little bit more detail, do a little bit more math, and hopefully make it a little bit easier to understand.
About 6,000 years ago. Okay, the moon is going around the Earth. Okay, did you know as the moon goes around, it's gradually getting farther away? We're slowly losing the moon. It's only a couple inches a year, about 3 inches a year, so it's no big deal, nothing to worry about. Now kids, this is going to be complicated, so listen carefully. The moon is getting farther from the Earth every year. So that means that it used to be closer. Well, if you bring the moon in closer, you start to create a problem because the moon causes the tides. Now you folks in Jacksonville probably have to worry about the tides, don't you? If a hurricane hits during high tide, you got a serious problem on your hand. Well, if you brought the moon in closer, the tides would be higher because of a law known as the inverse square law. If you brought the moon into 1/3 the distance, you take the 1/3, inverse it, and square it, it's 9 times the gravitational pull. And if you run all the math on this, you'll find out about 1.2 billion years ago, the moon was whizzing around just above the surface of the Earth. Now, way before that, you're going to have a serious tide problem.
Obviously, he's wrong, and I'm going to explain why. I'm going to list out the variables I'll use and their values. Values first. Here we go. In this case, C is 230,000 miles away. R is 1.5 because that's how fast the moon moves away from us every year. Y is 1.8 times 10 to the 9th. That means 1.8 billion years. I is a constant, 63,360 inches in a mile. G is unknown, that's what we're solving for. T is 2, and SL is what we're solving for in the other equation. In the equation I'm going to write, C is the current distance, R is the rate of decay, Y is the number of years, I is inches in a mile, G is gravitational pull, T is tidal range, and SL is sea level. So to find the gravitational effect of the moon on the Earth from 1.8 billion years ago, the equation is 1 over C minus RY over I over C squared equals G. And to find how high the tides would be on average, we need to know how high they are right now. On average, the tidal range from low tide to high tide is about 2 feet. So that's the number that we're going to be working with. T will equal 2. So to figure out how much higher the tide would be if the moon were that much closer, the equation is G times 1/2 T equals SL. So we've got 230,000 minus 1.5 times 1.8 times 10 to the 9th over 63,360 over 230,000 squared. That equals 1 over 230,000 minus 42,613 over 230, which equals 1 over 0.814726 squared, which equals 1.5065. So the tidal effect on the Earth 1.8 billion years ago is 1.5065 times as strong as it is now. Now let's figure out how much higher the tides would have been. So to figure out how much higher the tide would be if the moon were that much closer, the equation is G times 1/2 T equals SL. G equals 1.5 and 1/2 T is 1, so 1.5 times 1 equals 1.5. The average tidal range right now on Earth is about 2 feet from the lowest point to the highest point on average. It goes higher in some places and lower in others, but 2 is the average. And we know that T is represented by the tidal range. That's why T equals 2 in this case. So Kent Hovind made a claim. He said 1.2 billion years ago, the moon would have been so close that the tides would have been covering the entire Earth. It would have been a complete mess. I just proved that wrong.